Hello, Algebra 2AB. Today we're going to go over some Chapter 10 review problems to get ready for our test, which is on basic statistics, data distributions, and probability. So let's get started. At the very top, you can see what problems we're going to be doing from this retake review guide. So let's start on the first one. All right, first we have the mean, median, mode, and identifying the outlier in the data set. So to find the mean, we've got to find the sum. Oops. Let's bring up my other tool. There we go. So we're going to find the sum. So 5 plus 24 plus 26 plus 27 plus 30 plus 21 plus 19 plus 29. And divide that sum by the amount of data values that we have in the data set, which is 8. So for the sum, we get 181 divided by 8, the amount of data values we have in the data set. And that's going to give us 22.6 for the average, or the mean. All right, now for the median, we have to arrange these values from least to greatest and find that value that's in the middle. So on the right side here, I'm going to start listing those values in order. So we have 5, 19, 21, 24, 26, 27, 29, and 30. All right, so then we're going to find that value in the middle, so we could go end to end. And then these are the two values in the middle. When we have an even data set, to find that value in the middle, we just find the average of these two. So the average of those two would be 25. It's 24 plus 26 divided by 2. Another easy way to find that would be, well, the middle value has to be 1 unit away from both. Okay, since 24 is 1 unit away from 25, 26 has to be 1 unit away from that middle value. So we get 25 for the median. And then for the mode, notice in this case, all of the data values appear the same amount of times. All right, so if they all appear an equal amount of times, we've got no mode. No value appears more frequently than the other values. And then identify the outlier. Okay, if we take a look at all these values are in the are close to the 20s. We've got a 30 and a 19, of course, but 5 really stands out. That's the one that's going to be skewing the data set a little bit. So we've got 5 as our outlier. All right, now let's go to number 3. All right, so for 3, it says find the range and standard deviation of the data set. All right, so we have only 6 values here in our data set. We're going to list these values in this left column here. All right, you can do that in order. You don't have to do it in order. That's up to you. I like to do it in order, so I'm going to have 10 go first, then 9, then 8, then 7, 5, and 3. Now, if we want to fill in this table, which is going to help us find that standard deviation, we need the average. So we need the average of these data values. So you can do that off to the side again. Oops. Accidentally clicked my pen. All right, and divide it by the amount of data values we have. Okay, if we do that, we get 7. So that 7 will go in that second column all the way down. Now for the third column, we're just finding the difference between our data value and the mean of the data set. All right, so 10 minus 7, that'd be 3. 9 minus 7 would be 2. 8 minus 7 would be 1. 7 minus 7 is 0. 5 minus 7 is negative 2. 3 minus 7 is negative 4. Now here in the fourth column, we're just going to square the third column. So this value, we're just going to square it and write it here. All right, so this is what's called the squared deviation. So we have 9, 4, 1, 0, 4, and 16. Remember, with our negative values, when we square that negative, it's going to be a positive. Negative times a negative is still a positive. So it really doesn't matter if these are positive values or negative values here in that third column. We're always going to get positive values here. All right, so now we want to find that total. Okay, because to find the standard deviation, we're going to be taking the square root of the sum of those squared deviations divided by n. All right, I'm just simplifying this here so we don't have to write out the whole formula. All right, so we want to add up all these values in that fourth column. If we do so, we get 34. And then once again, from our mean, we know there's 6 data values here, so we can just plug that in to find the standard deviation. So we have the square root of 31 on 6. All right, so if we find the square root of 31 on 6, we get about 2.38. Now for the range, that's just the biggest value minus the smallest value. Now if you listed them in order, that's going to be pretty simple. All right, it's going to be the first one, if that first one is the largest value, the first one minus that last one. So 10 minus 3 gives us 7. That's the span in the data set. All right, let's move on to the next one. So we got some tricky examples ahead. These are the tricksters. So for number 4, it says find the value of x. And all it tells you is 4 data values, and it's missing a data value in this data set. But it does tell you the mean. With that mean, we can find that missing value. All right, so this is how we would naturally or normally find the mean. We'd add them all up and divide by how many there are. Now we've got 4 values, but we've also got another value which we're looking for. So we're going to write plus x divided by 5. All right, so that sum divided by 5 would give us this mean, that 80.5. Now we can work backwards. So if we're solving for x here, we got to get rid of this division. So multiply by 5. All right, at the same time, we can combine these constants together. So we'd get 326 plus x equals 402.5. All right, so now subtract 326, and that missing value is 76.5. Now, number 4 often gets mixed up with number 5, where it says the median is 30. So we got to know what the median is. Remember, the median is the middle value. So that's the one that divides the data set in half. So it's saying this middle value right here is 30, and we want to find x. All right, we can do this the more mathy way, or we can do it the more common sense way. The mathy way is, well, to get the median, we would take the average of these 2 values. All right, so that's x plus 24 divided by 2. That gives us that 30, which is the median. Now we can work backwards and solve, so multiply by 2. Subtract 24, and we get 36. The more common sense approach, and one that I highly advise, is, well, if this value is 6 units away from the median, that value's got to be 6 units away from the median. So all we got to do is add 6. There we go. We get our 36. That way we can avoid some potential errors by not actually doing, the whole formula. All right, so let's move on to the next one. All right, so we got 6. All right, this one's going to take a little bit longer because we have to actually make a graph for this one. All right, so we're going to use the following table to make a histogram. Now, those intervals are key on the left side. So these intervals are going to be how we're going to construct what is essentially our x-axis here. All right, it's not really our x-axis. It's going to be treated pretty much like our x-axis. And what we're going to do is use those values on the left side. So 1, 6, 11, 16, 21. And we actually need one more because that bar that's going to represent that 21 to 25 interval is going to go right here. So we need one more, and that's going to start where the next interval would start, which is 26. Okay, now we just have to construct the frequency portion, which would be like the y-axis. All right, so all these are even. We could easily just go up by 2s, so that's what I'm going to do. It's 2, 4, 6, 8, 10, 12, 14. That's enough for what we're trying to do here. So 2, 4, 6, 8, 10, 12, and that'll be 14. All right, now we just do the best that we can. I would highly advise using a ruler. Of course, if you're, a good artist, which I am not, maybe you don't need one. Okay, so there's our 10. Here's our 14. Here's our 12. And then we got 2 2s. Here we go. Now, based on this, we want to describe the shape of the distribution. All right, it's either going to be symmetrical, skewed right, or skewed left. Okay, in this case, if we connected, the top or the corners of this graph, we'd see most of the data is right here, but there's some data values over here that are skewing this data set. So that would be skewed to the right. All right, we can essentially say that here's some outliers over here that are skewing our data set. All right, now we're getting into more of the data distribution and data displays. So first, let's tell whether the data are qualitative or quantitative. So height of Major League Baseball players. The key part in that is in determining this is quantitative means it's an actual measurement, whereas qualitative are more like descriptors describing the data set. All right, so height of Major League Baseball players. Okay, that would be quantitative. Okay, because we're actually measuring something. We're measuring how tall, quantitative, measuring how tall those baseball players are. That's a measurement. We use a ruler, yardstick, whatever, and we're actually measuring something there. Okay, for the next one, names of people you work with. All right, when we're listing out the names of the different people that we work with, that's not a measurement. Okay, that's just their different names. It's describing them, so that would be qualitative data. All right, now based on these decisions, based on whether it's qualitative or quantitative data, that might change the type of display that we're using. All right, now for these, there is no one right answer. Okay, there's many different answers, many different ways that we could properly display the data that we have. But we want to explain our reasoning and be justified and make sure that we could actually use that data display with this type of data. So if we take a look at 10, it says comparison of eye color of students in a classroom. Now, one of the first things that come to mind, it's not the only thing, but one of the first things that comes to mind for me is just a bar graph. Okay, so we could have, all those who have brown eyes. We could have all those who have blue eyes and whatever else over here. And that's how we could display that type of data. Let's say green, even though that's rare. All right, and 11, choose an appropriate data display for ages of kids at daycare. Okay, for something like this, we could construct intervals like we saw with number 6 when we were making a histogram. So with that, if we constructed a table with intervals, we could draw a histogram for that. Okay, where you have, intervals like this, then you got your frequency, which is talking about how many people are there. All right, something pretty simple. All right, let's move on. Okay, so now we're going to talk about counting things so that we can get into probability. All right, for 16, you're choosing a password that has 3 letters followed by 2 digits. So we're going to have 3 letters followed by 2 digits in this password. And it says how many passwords are possible if letters and digits can be repeated. So that means if we use a letter, we can use it again. If we use a digit, we can use it again. Right, so for this, we just have to figure out, okay, how many letters are there in the alphabet? There's 26. Right, if we pick T, we can pick T again. So in the second spot of the password, we've got another 26 options. In the third spot, we've got another 26. Okay, it's followed by 2 digits. So we have 10 digits to choose from. Well, let's say we choose 5, we can choose it again. So we still have 10 options for the fifth spot in that password. So that's 26 times 26 times 26 times 10 times 10. If we do that in the calculator, we get 1,757,600 different passwords that we could create with those stipulations. For part B, we're still creating the same length password, but now we have some restrictions here. Okay, the things that we use cannot be repeated, or sorry, the letters and digits cannot be repeated. So we still have 26 options for the first letter, but if we choose T, we can't choose T again. Therefore, we have one less option for the second spot in the password. All right, then for the third character in the password, you know, if we chose M second, we can't choose T or M, so now we have 24 options. All right, same thing for the digits. We still have 10 for the first digit, but if we choose 5, we can't choose it again, so that means we have 9 options. All right, so that brings 1,404,000 different passwords that we could create with those stipulations. All right, so you can tell, like I've said before, more restrictions, okay, or more stipulations would leave a password a little bit less secure. Okay, of course, when we're talking about creating real-life passwords, they have restrictions, but usually those restrictions are to ensure that there's more possibilities for each character. You know, you can have special characters, you can have numbers, letters, capitalized, uncapitalized, and that actually gives you more options with every single one of these characters in your password. All right, let's move on to 19. So it says, tell whether the number of possibilities can be found using a permutation or a combination. All right, remember, key thing about this is for a permutation, order matters. All right, for a combination, it's not the order that matters, it's the group that matters. So when we're talking about permutations, we're talking about different orders. When we're talking about combinations, we're talking about different groups. All right, so if we take a look at 19, it says, how many ways can 10 runners finish a race in first through third place? We have to think about the context of the problem. Does order matter? And of course, if it's a race, of course order matters. All right, first is not the same thing as second, which is not the same thing as third. All right, so that means order matters. So this is definitely a permutation. And of 10 runners, we're trying to figure out how many different ways can we order 3 people. So that's 10p3. Right, if we do that, that's 720. Another way to do that, we don't have to use permutations. We could think about it the same way that we did that password example. We're just concerned about these people that finish first, second, and third. And of 10 runners, 10 different people could finish first. And then once that person crosses the finish line, we've got 9 different people that could finish second. Once that person crosses, we've got 8 different people that could finish third. So that also gives us 720. All right, but keep it short and simple. Let's use that permutation key in the calculator. All right, for 20, Pizza Palace has 10 toppings for pizza. You want 4 toppings, all different. How many 4-topping pizzas are there for your order? So we want to figure out how many different pizzas can we order here. All right, and once again, we have to figure out, does order matter? All right, in this case, order doesn't matter. Okay, those toppings are going to be put on the pizza, so it's just the group that matters. So that means this is a combination. Okay, so that means of 10 different types of toppings, we're figuring out how many groups that have four different toppings. So that's 10C4 So that's 210. All right, we're getting there, folks. All right, so we're going to do a bunch of probability types of problems. All right, because that's basically one of the focuses of this chapter. With that, so we determined how to count things. So that means we can figure out the number of different ways something can happen, and also the number of total outcomes. All right, and that's how we find the probability. Right? The probability of some event is just going to be the number of different ways that event can happen divided by the number of possible outcomes of that experiment. So if we take a look at 21, what's the probability that it lands on 1? Well, we've got 1, 2, 3, 4 ones. So that is 4 out of, if we count up all these spaces, 12 spaces. So that gives us 1/3. 0.33 or 33.3%. All right, you can write any of these as a fraction, decimal, or percentage. Okay, they're all equivalent. All right, it's just up to your personal preference. All right, so in the next problem it says, what's the probability that the spinner lands on an even number? We have to count up the even numbers. All right, so we have 1, 2, 3, 4, 5. All right, so that's going to be 5 out of 12, and we could just leave it at that. Probability is 5 out of 12. All right, now let's talk about these dastardly card problems. I love these problems, but I know, especially if you don't play cards, these can be really tricky. So if we want to figure out the probability of selecting a 3 when we're drawing just one card from a standard 52 card deck, we have to figure out how many 3s are in the deck and then how many total cards are there. So if we take a look to the right as just a little guide, we've got 4 3s in a deck, 3 of spades, 3 of hearts, 3 diamonds, 3 of clubs out of the 52 total cards. And if we simplify that fraction, we get 1/13. That's our chance. All right, if we want to find the probability that we draw a spade or a club, that means we have to add up all these spades. All right, we got to add up all these clubs. All right. One cool thing about a standard deck of 52 cards is, a quarter of the deck is spades, a quarter is hearts, a quarter is diamonds, a quarter is clubs. So that's 13 spades and 13 clubs that we could draw. So that's 26 out of 52. Which would be half the deck. Okay, then for 25, that's very similar to 23. We just got to figure out how many aces are in the deck. There's also 4 aces. So that's 4 out of 52, which is 1/13 again. Then how many hearts are there? That's 13, a fourth of the deck. And that's why we get a fourth when we simplify that fraction. All right, for 27, we want to figure out what's the probability of getting a king or a heart. This one's tricky now. So if we circle all the kings, and then we circle all the hearts, notice we can't just add up 4 kings plus the 13 hearts, because we'd be double counting this king of hearts. Okay, so there's 2 different things we could do. All right, we could just add up all the kings plus all the hearts, and then subtract the amount of times we double counted, all right, which would be like the overlap between those 2 events. Or, of course, if we have this picture, we could just count them up. All right, if we just count them up, we get 16. That's 16 out of 52, which would be 4/13. All right, so you can see how some of these will get a little tricky. All right, we're almost there, but we're not done yet. Let's take a look at 28. This problem, now we're talking about geometric probability. So it says, find the probability that a dart thrown at the target will hit the shaded region. Assume that the dart is equally likely to hit any point on the target. Okay, so there's a lot of assumptions being made here in this question. we're saying we're good enough to hit that square, okay, and every single place on that square is equally likely to hit. That's probably a really big assumption there. Okay, so basically what this question is asking is it's asking us to find, whoops, let's undo, the probability that a randomly point selected within that square lies in the shaded region. That's what it's asking. Now to figure out the probability that a randomly selected point lies in the shaded region, we just have to figure out the area of the shaded region and divide it by the area of the total figure. Now we have different figures here. So the area of the shaded region is that triangle. So we can really say we just got to figure out the area of the triangle divided by the area of the total region, and that total region is really a square. So if we can find the area of that triangle and the area of the square, we can find the probability that a randomly selected point lies in the shaded region. All right, so the area of a triangle, just as a reminder, 1/2 base times height. All right, the area of a square is also, square, there we go, is also base times height, length times width, or side length squared. All right, so now let's just plug in some of the information that we have. So the area of this triangle is going to be 1/2 base times the height, so that's 4 times 3. And then the area of the square is just side length squared, so the side length is 7, so that's just 7 squared. All right, and if we compute this, that's 6 out of 49. All right, now that doesn't give us really any good context as to what our chances are of hitting the bullseye or hitting the target. So we could write this as a percent, so type in 6 out of 49, or 6 divided by 49 in your calculator, multiply by 100, and we get 12.2%. So that's our likelihood of hitting the target there. All right, in 29, Bob conducted a survey of students' hair color in his classes. The table shows the results. Find the probability of each hair color. So this is experimental data here that's collected from a survey. If we add up all these numbers here, that'll get the amount of people that Bob surveyed. We get 76 as a total. Okay, so each one of these is going to be out of 76. All right, so the probability that someone has black hair is the amount of people that had black hair, 16, divided by the total amount of people that were surveyed, 76. Okay, if we did that, we'd get 21.1%. The probability someone has brown hair is going to be 48 out of 76. And if we do that, we get 63.2%. The probability someone has blonde hair is going to be 10 out of 76. 13.2%. And then the probability that someone from this survey has red hair, that's 2 out of 76, which is 2.6%. All right, a couple more. All right, if we take a look at 30, it says a 6-sided die is rolled. What is the probability that the number rolled is a 2 or less, or is greater than 4? Okay, on a die we have six possible outcomes. All right, and then if we want to figure out what's the probability that the number rolled is a 2 or less, or is greater than 4, we're going to add these possible outcomes up. So how many different sides are 2 or less? Well, that's 2. We can get a 1 or a 2 when we roll that die. Or greater than 4, that's 5 or 6. So that's another 2. So that's 2 plus 2 on 6, 4 on 6, 2/3, which would be about 66.7%. Right, so this was an example of a disjoint event. Remember, a disjoint event means that those events are mutually exclusive. All right, remember, mutually exclusive means they can't both occur at the same time. All right, so we were just able to add these two up because they can't both occur at the same time. If they could both occur at the same time, then we would have to subtract the overlapping region, okay, the events in which we double counted. All right, so the probability of A or B occurring in 31 is just going to be the probability of A plus the probability of B. Pretty simple. So we get 0.86. And the next example, all right, we have to determine whether the events are disjoint or not. Okay, so how we're going to determine that is whether the probability of A or B is simply the sum of the probability of A plus the probability of B. We can see that's not the case. Okay, and just in reference, this one is not a great example because it doesn't really make sense in terms of the real life context. So this is not disjoint. Oops. This is overlapping. Okay, so since it's overlapping, the probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B occurring. All right, that would be the overlapping portion. Okay, so we're given all these values but one, so we can plug those other values in. So we get 0.22 equals 0.57 plus 0.1 minus the probability of A and B occurring. I'm just going to put an X there because that's what we're looking for. All right, and we're going to make it simple. All right, so we could combine 0.57 plus 0.1, we'd get 0.67, and now we're just going to solve for X. So subtract 0.67 here, we get negative 0.45, but that equals negative X. So we're going to divide by negative 1, and we get X equals 0.45. All right, so the probability of A and B occurring in this case is 0.45. And that's why I said it's not a realistic example, because this probability is greater than that probability, which doesn't make any sense in terms of the context of a problem. All right, for 35, the probability of not A. Now, the probability of not A just means the probability that A does not happen. All right, so if the probability of A is 0.92 or 92%, all right, the probability that A doesn't happen is everything else. All right, so we could just do 1 minus 0.92, and that gives us 0.08, all right, or 8%. If the chances of A happening are 92%, the chances it doesn't happen is 8%. Makes sense. All right, let's move on. Okay, I said we had a couple, and that was like a couple ago. We got 3 more left. All right, these are the last 3. So in 38, it says of 28 students, 18 have a dog and 14 have a cat. In all, 12 of the 28 have a dog or cat. What is the probability that any one of the 28 has a dog and a cat? Now, once again, also another unrealistic example. If you just think about it a little bit, you can see that this doesn't make sense. But we're just going to use the formula and find the probability that any one of them has a dog and a cat. So remember, our equation for overlapping events was the probability of A or B equals the probability of A plus the probability of B. Whoops. Okay, got to go back there. Pen's being messed up a little bit. So probability of A plus the probability of B minus the probability of A and B. All right, this is the one that we don't have. We can put X in for that one. For the others, we could totally write the fraction, but we really don't have to. Okay, I'm going to write the fraction anyway. So A or B. It says 12 of the 28, or 12 out of 28, have a dog or cat. Okay, let's say event A is having a dog, event B is having a cat. So that's 18 out of 28. 14 out of 28. Let's combine these fractions. We get 32 out of 28, which is one reason, perhaps, why it doesn't make sense in the context of the problem. This can happen for overlapping events, that it's greater than the total, but once again, like I said before, this is not very realistic. All right, so if we subtract 32 28ths from 12 28ths, we get negative 20 28ths. So x is actually positive 20 over 28, and if we write that, type that out in our calculator and write down the percent, we get 71.4%. All right, last two. All right, you have an equally likely chance of choosing any integer from 1 to 30. Find the probability of the given event. All right, so 39 is, it states a multiple of 3 is chosen. So we have to figure out how many multiples of 3 there are from 1 to 30. Okay, so we could list them out. 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. So that was 10, which makes sense. Okay, it's going from 1 to 30. We're talking about multiples of 3, so that's 10 out of 30 possible outcomes, which would be 1/3. All right, then for 40, a number less than 10 is chosen. So if we think about the numbers that are less than 10, that means 1 through 9. There's 9 numbers there out of 30, so that's 9/30. All right, folks, I know that was a long video. Hopefully that helps you in preparation for the test. All right, and have a great day.